제가 고쳐줬어. 아직 안 됐어요, 그거? 아직 안 맞추는 거 같아요. 그건 무시고, 를 아, 저번 신문에 한번 더. 일단,
네, 다시 하겠습니다.
What's the power?
No, the first thing with my friend, I'm like, what's the bird missing the glass that they
엎드려 내려. Okay. So did nice online class this morning. Then so all the top project presentation is productive. So we started grading. We're PA. Homework 2 will be out probably this evening. And midterm exam, how to midterm exam is delivered, right? Any question? Then we can go on to hydrostatics. Yes, okay, regularly, made by now. So, 이거요, 그래도 쓰고, 나랑 같이만 말고. Hey, good afternoon, everyone. My name is Young Cho, and today's lecture is about ship hydrostatics. Specifically, buoyancy is a key point in hydrostatic, so I will explain it. First, let's talk about solids and fluids. From the perspective of fluid dynamics, all matter can be classified into two states, solids and fluids. And solid can be deformed by an external force and can resist the external force. So we can define the displacement of solid. However, fluid cannot resist by the shear stress, and fluid is a substance that can be deformed continuously under the application of the shear stress. So it is meaningless to define the displacement to the fluid. So instead, we can define the velocity gradient of the fluid. And this is labor architecture ocean engineering class. So we will cover only fluid, cover about fluid. And as you may know, there are a lot of types of fluid, such as liquids, gases, plasmas, and even plastic solids. And today we'll focus on liquids and gases. Before discussing about liquid and gases, I will explain about three terms: density, pressure, and viscosity. And we are already familiar with these terms. So first, I will explain about density. Density is defined as mass per unit volume and is dependent on pressure and temperature. And generally, the liquid of density is 1,000 times greater than that of gases. Next is pressure. Pressure is defined as force per unit area with units Pascal, bars, ATM, and so on. And this is the pressure is the hydrostatic force, which is acting on static fluid. So I will explain it more detail later. Last is viscosity. Viscosity is a measurement of fluid's resistance to flow. So for example, moving through the air is easy, but moving through the water is difficult. So we can call the fluid is thin if it has low viscosity and thick if it has high viscosity. So we have dealt with these three terms, and let's talk about the differences between liquids and gases according to these terms. So let's look at the change of density under the change of pressure. So first, the gases. Gas varies significantly under the change of pressure, so we can call it compressible fluid. And on the other hand, liquids can be assumed to remain constant under the change of pressure, so we can call it incompressible fluid. So there are notable differences between hydrodynamics and aerodynamics. And then let's discuss about how the pressure is applied in the static fluid. In a static fluid, pressure at any given depth is the same, and the pressure increases with depth. And is always applied perpendicular to the surface. And the hydrostatic force can be calculated by integrating the pressure at given point over the surface of a object like this. And the submerged object always experience upward force, which is called buoyant force. And buoyant force equal to weight of displaced water. And this principle applies both fully submerged and partially submerged object. So for example, the iceberg. As you can see, iceberg has a lot of submerged volume, so it will experience a lot of buoyant force. And similarly, submarine can dive and float on the surface due to the same principle of buoyancy. So let's watch about how submarine dive and float.
They can reach depths of about 800 feet thanks to a system of internal and external ballast tanks.
We have 5 external ballast tanks that are normally filled with air when I'm riding on the surface. When it is time for us to dive, we'll open vents on those ballast tanks. There's grates on the bottom of the ship that allow water to come in, displace the air, making the ship just slightly negatively buoyant. We then proceed down to the depth that we want to go to. And we use internal ballast tanks to make the ship neutrally buoyant, that then we can progress on our way whatever depth we choose.
The crew on board the Virginia class have an abundance of cutting-edge controls at their fingertips, one of which is replacing the most iconic feature in submarine history. The periscope has been a key component on the submarine for over 100 years, but engineers on the Virginia class are taking a bold step toward the future by replacing the periscope with a state-of-the-art photonic mast.
The photonic system is a mast with a sophisticated camera system that allows what would normally be displayed just in a periscope to be displayed on widescreen monitors throughout the ship.
And it used to have an optical periscope that came down, which drove the construction of the submarine and the orientation of all of the rooms on the submarine.
Bulky periscopes force most submarine control rooms to be located on a cramped upper deck. On the Virginia class, the compact imaging equipment is housed in a part of the submarine known as the sail. This allows the sub's control room to be built on the wider second deck.
My control room that I'm standing in right now houses all of the important decision makers. It really brings the crew together to operate as a team, as a unit.
Okay. Next, we'll talk about stability of a system. There are three states of equilibrium: stable, neutral, and unstable. To determine the stability of system, we slightly disturb and observe whether it returns to its original position. So we can say a ship is stable. It returns to its initial upright position. And if the ship is unstable, it can be capsized, like this image. So as you can see on the screen, it is very unstable state. And on the right side of the picture, the ship is overrolling due to the instability, as we learned in this morning class. And the unstable state can be occurred by the system's high center of gravity. So if the system has high center of gravity, it can be the system can be unstable. So it is important to lower the center of gravity to prevent the ship from capsizing. Okay, let's watch video about ship stability.
Vessel's ability to return to an upright position section of a ship. Stability is the vessel's ability to return to an upright position after being heeled by an external force. For a ship to float, it must displace a mass of water equal to its own mass. Dead weight is a measurement of the ship's total carrying capacity. It is the total weight of cargo, fuel oils, provisions, crew, fresh water, stores, and so on. TPC, tons per centimetre immersion, is a measurement of how many tons that are required to change the ship's draft by 1 centimetre. The TPC may vary at different drafts and trim conditions. K is the abbreviation of the keel and is always at the same place. This is on the constructed line going through the centre of the ship, called the centre line. G is the centre of gravity, and its vertical placement is dependent on the placement of masses on board. Heavy cargo placed near the bottom of the ship gives a low G, while cargo placed higher in the ship gives a higher G. The gravitational forces work downwards as if they work in one point. The forces of buoyancy work all over the underwater hull. These forces of buoyancy work upwards, as in one point, called the centre of buoyancy, B. M is the meter centre of the ship. When heeling, at small angles, the ship will pivot around this point. Its importance and placement will be explained in the next chapter. Perpendiculars are constructed vertical lines forward and aft, used for measurement purposes. The forward perpendicular goes through the forward end point of the constructed waterline. The aft perpendicular goes through the rudder shaft. In calculations, the length between the perpendiculars is often used and referred to as LPP. In the middle of the perpendiculars, we have the so-called mid-length of the ship. This is found by dividing the distance LPP in two. LCG is the centre of longitudinal gravity, and its placement is dependent on the longitudinal placement of masses on board. Normally, LCG is measured in metres from the aft perpendicular. LCB are forces of buoyancy working all over the hull, as described earlier. These forces work upwards as in one point. Normally, LCB is measured in metres from the aft perpendiculars. When changing trim, a ship will rotate about a transverse axis that passes through the centre of the actual waterline. This centre is called longitudinal centre of flotation, LCF. LCF is read out from the hydrostatic data of the ship at the given conditions. This is an example of a ship rotating about LCF. The block coefficient is a measurement of how much an underwater
for your attention, and if you have any questions, please raise your hand. Thank you. Great.
This video is good. Right? It's long and have many contents. See the second part of the hydrostatics. And metacenter, see M. Metacenter height is a GM. Actually, it is a distance between G and M. Traditionally or historically, they call this height. Chart shows again the center of gravity is G, CG, center of gravity CG or G. Okay. As a good picture, it is G, and center of buoyancy is B. So G is a total weight of the ship itself. Total weight of the ship. And center is different. And buoyancy is coming from displaced to water. Right? Body weight is coming from whole ship. So it typically goes up, right? This portion is included in the CG, this portion. But B is only submerged portion, displaced water. Right? The center of displaced water is a B. That's why usually B is higher. And floating body angle of heel cause the center of buoyancy to move. Say rotation, or wind blowing, or wave is coming. Somehow but usually they healing due to rotation, maneuvering. Anyway, it is happening. Then submerged body shape is different. So the center of displaced water is changed. volume should be same because it is a balance between weight and buoyancy. Always, it is balancing. Total weight, total buoyancy is balancing. But there is change because of the motion. Turning is also another motion. Heeling is another motion. It is slow, it is quick, but it is motion, dynamic. In any point, the balance should be same. The balance is changing because of timing. That's why they are moving. But when water has come, then it return back to the original position state. And this is changed so that buoyancy force weight is still there somewhere here. Where is which very here? G is not moving. Nearly not moving. If myself is moving on the back, a person is moving on the back, then very small portion of G center is changing, but it is negligible. If there is a massive movement of cargo due to some motion, then G should be changed, noticeably changed, but not so much as this change. So usually we assume that G is staying there, position is staying fixed, even though I'm moving, it is negligible. But B is moving every time. That's why the M, but M is crossing point, one crossing point. B crossing point. It should be changed. M should be changed. But usually they found that in a small angle over here, the M is typically stable, one single point, not change much, negligible changes. M also. That's why they saying GM is important for the stability. Even though G is negligibly fixed, right? Fixed point. M is moving, but still also we can assume that it is fixed. Or small angle. That's why GM is chosen to be the representative for stability check. Yes, sir. Data center is similar to rocking chair. 3G of rocking chair may be empty one. It should be empty one also. Person is sitting, there's a seat should be changing. Anyway, the support should be the buoyancy. This is not buoyancy, but we call support. So they have differences when there is rocking is going, tipping over, right? Intersection. It's very similar to this. G is moving. M is slightly moving. We assume that this is for small angular inclination. So meters and height have been to be historically the representative value of distance was showing the stability performance of the ship. Distance between G and M. Positive, we saying stable. Negative, unstable. As you see from previous slide, it is stable. This is not unstable, right? So I say calculating GM, we assume that the ship is stable. Small head angle, essentially or nearly constant. G also changing, M also changing, but very small changes. It's essentially stable or constant. And GG is a sine theta. It is calculated when GG is distance. So it is writing when you calculate the moment, you need to calculate the arm multiplied by force, right? So arm, the writing arm is GG. This is a value to be used for the calculation of writing arm or reverse restoring moment. Before this is writing arm. Here's another video, I guess. Let's see. This one's
Metacenter. When a solid body floating in a fluid is tilted from its equilibrium position, then the stability of its equilibrium depends upon the location of its metacenter. To understand this, let us recall that a solid body floats in a fluid. If the mass density of a body is less than that of fluid, as in case of wood, plastic, ice cube, etc., and if the weight of fluid displaced by the immersed body is equal to the weight of the body, as in case of boat, ship, etc., when a body, say a ship, floats in water, it is acted upon by two forces. A vertical downward force of gravity, which is equivalent to the weight of the body, W, acting at the center of gravity, G, and an upward vertical buoyancy force, Fb, which is equal to the weight of the water displaced by the immersed body, which passes through the centroid of the displaced volume of water, that is, the center of buoyancy. Now, for a floating body to be in equilibrium, the buoyancy force should be equal to the weight of the body. Also, the center of gravity and the center of buoyancy should lie on the same vertical line, called the center line, BG. Now, if a body undergoes an angular displacement, say in the rightward direction, then we see that the volume displaced is larger in the right side. Thus, the center of buoyancy shifts towards the right from B to B dash, and a couple is formed which tries to rotate the body. Here, the point of intersection of the vertical line through the new center of buoyancy B dash and the center line BG is termed as the metacenter of the body, and the distance by which the metacenter lies above the center of gravity of a floating body is known as the metacentric height, GM, which is given by. Depending upon the location of the metacenter, a floating body possesses three types of equilibrium. They are stable, unstable, and neutral equilibrium. When M is above G, then in this case, a restoring couple is formed by the buoyancy force and the weight of the body, which tends to turn the body to its original position. Thus, the body is said to be in stable equilibrium. Now, when M is below G,
okay. Can watch. So, how can you calculate the GM as a designer at the beginning of the design stage? Ship is not appearing yet, not constructed yet. The ship is only staying as a drawing or CAD model. You need to calculate, right? GM, the stability check, performance, very important. So it is historically they tried to many different ways, but arrive at this idea of AB, BM, AG, KB, BM, M, BM, and KG. KG. So we want to calculate the GM, right? KB, BM, and KG. AB, BM, BG. Remain GM. Very simple. Right? B is moving. B is moving. Right? G is not moving. So you can say this is constant. B is moving. You need to calculate. So by knowing the V, the healing angle, you can calculate by your hand or by using computer. Because design is there. Right? Design is there. In drawing or in the CAD system, the shape of the ship is drawn by myself, the designer. So you can calculate B or B prime. If you know, so you usually I put, say, to the computer at heel angle of 1 degree, 2 degree, 3 degree, 4 degree, 5 degree. Every degree, please calculate B. Right? Computer do for yourself. When I was young, I do myself. Very tedious calculations. Right? Anyway, you can do that. EM is something like this. And volume of displacement is constant. You already know. It is the same as G, the total weight, right? Total weight is changing when there is a cargo loading and unloading. But once loading is finished and the ship is leaving from the port, then everything is stable, constant. The weight is constant. But when they go to the port, you load, unload cargo, the changes, right? And also there are small changes like fuel, oil, and water. You drink water, something like that. Very, very small ones. And myself is moving, but it is negligible. Volume displacement is constant. Moment of inertia of the water plane area. This is water plane area. Water line. Water plane area should be including long distance. This is also changing. Right? The area, the shape is changing. So that what we can calculate, same as this B. So that can be calculatable, right? That's why we can arrive at this. For each angle of here, angle of here, you can calculate this. Is it okay? Right? It was very difficult to work for designers and workers. Inclining experiment. When ship is constructed, then even though designers want to know the real value of the weight, because I designed it in this way, but shipbuilders do a little bit differently. I say it should be steel plate of 2 centimeter in this area, and this area 1.5 centimeter thickness of plate, and pillars are there. You can think about this construction of this building. As a designer of this building, the construction is a little bit different, right? So we need to check whether this is a survey. Every construction site, there is a separate company or person who is surveying construction, and surveying is a different person. Designer is also different, right? Similar to this. And then, there's a video. The inclining experiment is done construction. Once ship is constructed,
Hello. In this video we're going to be exploring the inclining experiment. So the inclining experiment is typically done to determine the kg of the vessel. It can be done for the light ship of the vessel. Typically it's done for the light ship. after a new build or after some kind of modification in a maintenance or yard period. The basic idea here is that you have a known weight. You might load it up on the center line. And on the ship, you will hang a pendulum, and you'll know exactly how long that pendulum is. And down at the bottom of the ship, you're going to set up, a kind of a wooden batten down there. And that pendulum will have a plumb weight on it. And then what you'll do is you'll take that weight, you'll know what the weight is, and you'll slide it a known distance to port or starboard. In this case, if you're looking at it from astern, the weight was, they slid the weight a known distance, from center line to starboard. And what happens then is that pendulum is deflected. It's deflected a certain distance, and you can actually measure it on the batten. You can draw a line there. So you have a line drawn for the center line, and then you have a line drawn after you've inclined it with a known weight and known distance off the center line. And now you have a deflection. And there's a ratio of the length of that pendulum and the deflection. And that we can relate that to this angle theta, which would be the angle of list created by that off-center weight. So let's look at this a little bit more carefully now. So in this picture here, this is our vessel. We're looking at it from astern. Here's our known weight. We're going to end up sliding it a known distance here to starboard. This line here is our pendulum, and our pendulum is actually lined up on the center line. We'll have this deflection here from where it was on the center line before inclination to where it is now after we inclined it. And so we have a ratio of this distance versus this distance. So we can measure those carefully. So batten deflection.
So as a designer, also as a ship owner who has a contract with the shipbuilder, everybody wants to know the exact weight of the ship once the construction is finished. Because it is important for the safety, GM. Also, it is important for the cargo capacity. If I want to load 10,000 ton of cargo, right? But ship is built, say, 100 ton heavier than I expected. Then cargo of 100 ton cannot be loaded because of the limitation of freeboard. That's why, as a ship owner, the cargo carrying capacity is important. It is contracted as a signed signature, contract signature. That's why we should check whether the exact weight of the ship and also the position of the weight, AG, for the stability. Also, if the ship is not stable, unstable, G is too high, then you cannot carry too much cargo. Also, not only for the weight, but also of the stability. That's why it is important. So if you know the weight, say 10 ton of weight and 10 meter of distance, calculate the heeling moment. Right? And also you measure the heeling angle. Then you can calculate the other things in reverse way. There's the way they are doing, and the free surface effect. If there is a tank, probably in the bottom of the ship, that carries fresh water for drinking or shower, and also fuel oil for the ship properly. When the ship is started the voyage, usually they are full of oils and full of fresh water. But as we say go to the United States, it takes about 2 weeks from Busan to LA. Right? Then the oil is consumed and fresh water is also used. Then lower down. But ship is healing, the more healing moment is increased because of the movement of fluid. If fluid is full, there is no movement. But it's going down, movement is different. So you should check for the stability also. So that, as I told you, that to calculate GM for each angle of hill. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think increasing GM, it says GZ rather than GM, but it's same, right? Sign says. And it increases ship is ceiling. Some point is decreased and somehow it is minus. Right? Not sure. So before this is a range of stability. Also area is important. Angle of hill and GG. So this one you should calculate for the stability. Longitudinal stability, it is not so important, but it is important for the motion of the ship and slamming. In this morning, we had a cheat quiz on slamming, right? Slamming is pitching, ship is wave is coming, ship is pitching, then slamming is on the bottom of the ship, hitting by the wave. So that this is trim. Trim is important for the trimming. And also flooding and subdivision, you see this is Titanic. Have you watched the Titanic film video? Yes? Any of you? Titanic video film? Only two of you? You should watch. Right. This is an iceberg. Right. This is a new ship. First voyage. Very new ship. 100 years old. 100 years old. More than 100 years. First trip from London, not UK to United States. The near United States, iceberg. They hit and then the crack on the skin of the ship. And then submergence, water is incoming, flooding. At that time, there was no watertight bulk. Bulkhead is something like this word. If this building is flooding, water is coming from window and door, and right? But if we can make that is watertight, then even though water is flooding, this room is empty. Right? Watertight means something. If Titanic is built as a watertight bulkhead and doors, then they will not sink. But at that time, there was not such a concept. That's why it goes down one by one. So it takes many hours sinking down. That's why the film is going on. The story can go on. Many stories are going on, right? Slow down. Anyway, we say this damage stability rather than intact stability. Before then, calculating GM, no damage, right? So we call this intact stability as a GM, only GM. But damage stability, it is different cases. Water is coming inside. So different calculation, similar but different. Flooding and subdivision, so bulkhead is important and doors are tight, watertight. And one compound standard is saying that even though one room is full of water, the ship must be safe. There is a regulation requirement. Even though there is heating of the hull, punctuation of the hull, so that one room is full of water, but still ship is safe. There is a requirement, one compound standard requirement. Stability of submarine is different. We say two cases. When submarine is on surface, then it is same as normal ship, right? Same as normal ship. But the shape is different. But calculation is same. But in submerged stability, submarine stability. There is no change of V or G same, but B also same. That's why they need to have a B should be above G. Above G. Reverse way. The surface ship usually G is above the B. But now here it should be, you must be B. B must be above. Oh, there's the. This is final video, I guess.
We were looking at the differences between ships and submarines. Firstly, most obviously there are huge implications in terms of buoyancy and displacement of nearly 19,000 tons. To put that into perspective, the Statue of Liberty is only 93 metres tall. On the surface, submarines are very similar to all other ships. As they slip beneath the waves, however, there are some very interesting and fascinating differences that we need to know about. Before we dive into that though, let me tell you about this video's sponsor, Conflict of Nations. Conflict of Nations is a free online PvP strategy game with up to 128 other players. You become a nation state and your goal is to take over the world using whatever strategy you like. Maybe you prefer diplomacy and forging alliances with powerful stability. With a ship, you just need to make sure the underwater part of your vessel displaces enough water to provide buoyancy to keep it afloat. Submarines, of course, are a little different. On the surface, just like a ship, the hull needs to displace enough water to provide positive buoyancy, but it also needs to be able to sink, so you need to be able to increase its displacement to make it weigh more than the water it displaces. It's actually quite simple. You just flood some ballast tanks, making the vessel heavier and less buoyant, basically so that it sinks. That's great for going down, but then when you're deep enough you need to be neutrally buoyant instead. You want the submarine to weigh the same as the water it displaces, so that it neither floats nor sinks. Again, it's quite simple, you just pump out a little ballast water using compressed air from cylinders. Done precisely enough, you can make the submarine weigh the exact same as the water it displaces, making it neutrally buoyant. So, that deals with the buoyancy, but what about stability? After all, a submarine still needs to remain upright when underwater. Remember how a ship uses form stability to stay upright? This just means that the shape or form of the hull provides a righting force whenever the ship leans over slightly. The underwater shape changes, shifting the centre of buoyancy, separating the force vectors, creating a moment to right the ship. This is how, counterintuitively, the centre of gravity can be above the centre of buoyancy. A submarine, however, can't do that. When it's fully submerged, its underwater shape remains constant no matter how far it leans over. Its centre of buoyancy doesn't move. Instead, you have to rely on keeping the centre of gravity below the centre of buoyancy. Your stability is provided.
2 points here. Neutral buoyancy is required for the submarine. Neutral buoyancy is your body. Your body is almost neutrally buoyant. When you try to submerge it down to the swimming pool, it is not easy, but you can do. Also, scuba diving, you did scuba diving. You need to have a weight in your belt to make your body neutrally buoyant. Neutral buoyancy. Same as the water weight, your body. Because you have a tank, air tank in here, you need to somehow measure so that you make your neutrally buoyant. So that easy to navigate inside the water, submerged water, easily. Otherwise, with your V underarm, you cannot dive into, right? Because of the buoyancy. Second is weight. So how can you make neutrally buoyant? You should have a ballast water tank is full. And when you want to be up to the surface, you empty the ballast water tank, then the submarine moving up, right? Naturally moving up. That is the way, so you need to pump and ballast water tank. Also making ballast tank in the bottom, you should have a G is down to the. That is a two. Right. See. Questions? Then we can move on to. I start the discussion session today. The biggest ship stability. This is my contest. I will briefly review about the previous lecture about the ship stability, and I prepared the quiz and discussion. There are three states of equilibrium in the ship: stable and neutral and unstable. The ship must be sufficiently stable, because if the ship is unstable, it will be submerged to the ocean. And when we see a ship is stable, float sunlight when at rest in still water, return to its initial sunlight position if given of light, temporary deflection to either side by some external force. If the ship is unstable, the return to initial position, and neutrally stable, the ship will stay inclined. And this is the concept of the metacentric height. The metacentric height is a measurement of the initial static stability of a floating body, and it is calculated as the difference between the center of gravity of the ship and its metacentric. If the ship is stable in stable equilibrium, the metacentric height will be positive value, and if the ship is unstable, the metacentric is negative, and if the ship is neutral state, metacentric height is zero. And this is, I prepared some video, but this is same as the previous professor showed to you, so I will skip this. And this is about the righting lever. It's related to the righting force of the ship. The righting force is the force that acts to return a ship to its unright position when it is being tilted by external force factors. And the righting lever is the horizontal distance between the ship's center of gravity and the center of buoyancy when the ship is tilted at a certain angle. And the righting force is calculated by weight of the ship, our outer product with the GZ distance, and it can be replaced to weight outer product with the metacentric height and sine theta. And I prepare some piece. So this point.
Search for remain. This. No. No. This time you will not no. It is. First, the answer. It shows the coloring of it. First, the concentrate shade. If you press more quickly, you can get more score. So batteries move toward the hillside. Sorry, data center is above the center of gravity. Next question. Next question. So the ship does not is not a factor of the function. Please that. Congratulations, Marco. Strategies discussion. Just know the rating level is the length of the it depend on the G jet. So if we increase the recovery force is increased so that the ship can be stable. So what's the effect of the ship has large G jet? What the advantage and disadvantage? Have to say something. Please raise your hand.
Advantage is when the ship is here, the ship will go to the original position.
Rapidly. Yes. That's good. the ship has large G-jet, if the ship is tilting slightly, even slightly, it can return to its original position as same as his sensor. 보용. When you have to say about this modification, the ship has like that it has weak dynamic stability, so a slight motion on the ship might affect the big tumbling, so passengers might feel uncomfortable about like a student. Yeah. Oh, yeah. Also, students when first rings here, so the ship motor will be like under that region. So under there, yeah. So warning sometimes and stuff. I think the longer restoring port will make the ships experience larger structural stress, and also it might hinder the maneuverability of because shift in buoyancy force might try to overcorrect ships motion. Not sure. And then you told me and I think it's enough for discussion. So I end my discussion session. Thank you for your time.
Please write down the answers to the slide set and then share with us. Yeah. Okay, very interesting also. Yes. About the last discussion, I would mention this. You can think about it looks like spring. I told you in the morning, hydrostatic spring. I know more than half of you has a rather suspension of the car. It's something like a spring. When there is a rough road, suspension is softening down this rough road, right? And I found that not today's car, but say 20 years ago, the car from Europe has stronger suspension than Japan or United States. So that probably the car from Japan or United States feel comfortable because cushion is good, right? Soft, even though rough road, the passenger does not feel about this. But if you go to the rear rough roads, we need to have a stronger suspension. For the paved road, soft suspension is good, better. But rough road, you need to have a stronger suspension, stronger spring. That's why somebody is saying passenger feels uncomfortable if you have a higher response spring. GM. But there is a need. There is a need for the big GM. For such a U.S. Coast Guard or every Coast Guard vessel, they need to have their duty even though there is a storm is coming, because disaster is more happening in the serious situation. Right? Rough sea, there is a capsized accident is coming. Patrol boat should go to the site, even though there is a big wave is coming. Right? That's why they make a special ship. We call this is a lollipop doll toy. I brought you at the water tank with the lollipop doll, right? The same as this theory. Right? We can make that kind of ship, and also they built such a ship, right? We call in Korean 오뚜기 ship, lollipop ship. It's built by somebody already. Right? The problem is same as they cannot capsize. Even though capsize, they stand up again. Even though water is going down, but it is going up, right? It's good. It's good. So no capsize. But the problem is inside the ship, the acceleration is very high. Response acceleration, right? Soft spring, hard spring, acceleration, response to the passenger is different, right? If the response is too high, the acceleration, the motion is big, right? Big acceleration big, the passenger cannot sustain. So you need to have a very strong string and also have the inside the ship. But Coast Guard needs to work at this point, so with the ship. Okay, that's enough. So then I will not be here next week. We will have exam, so I will see you on 2 weeks. Have a nice meeting.